Continuing our study of integration by partial fractions, we're going to look at the first case, the case where the factorization of the bottom contains only non-repeated linear factors. So we've seen that when we want to integrate a quotient of polynomials, in other words a rational function, the first thing to do is to use long division in the case where the degree of the top is not less than the degree of the bottom. And that reduces the problem to integrating a partial fraction where we have this property that the degree of the top is less than the degree of the bottom. Then we factor the bottom part, q of x, and in this video we focus on the case where the factorization contains only non-repeated linear factors. So none of these factors are the same. And the only thing to remember about that is that if q of x factors that way, then our fraction r of x over q can be written as a sum of partial fractions of the form a1 over the first factor plus a2 over the second factor plus a3 over the third factor and so on. So in other words, we need to find the constants a1, a2 through an, one constant for each of the non-repeated linear factors appearing in the factorization of q. Okay, let's look at what that means on an example. Let's say we want to integrate the function x squared plus 2x minus 1 divided by x cubed minus x. You see that the degree at the top is 2, degree at the bottom is 3, so we're already in the case where the degree at the top is less than the degree at the bottom, so we don't need long division here. So we go to the second step, which is to factor the bottom. Of course we can factor x, so we get x times x squared minus 1, which factors further into x minus 1, x plus 1. So here we have three linear factors, x, x minus 1 and x plus 1, that are non-repeated. According to what we have seen, that means that there is a decomposition into partial fractions of the form a over x plus b over x minus 1 plus c over x plus 1, where a, b, c are real numbers that we have to find. And to find these numbers, we're going to look at two methods. The so-called n-cover method, that is the most efficient for this particular case, but has a limitation of applying only, at least in a straightforward form, applying only in that case where we have only non-repeated linear factors. And the system method that applies more systematically, and therefore even though it's not the most efficient method in that case, we're going to already talk about it a little bit. So let's start with the n-cover method. We want to find a, b, c. To find a, we're going to multiply both sides of the last equality by x, which means that on the left hand side we can cancel one x at the bottom. On the right hand side I have ax over x, so x cancels at the bottom. And then for b over x minus 1 and c over x plus 1, I multiply by x. And then we set x to the value that makes x 0, so in that case just x equals 0. And if I plug x equals 0 in what remains, on the right hand side I get 0 for the term containing b and 0 for the term containing c, so the only thing left on the right hand side is a. On the left hand side, when I plug x equals 0, I get negative 1 at the top and negative 1 times 1 at the bottom. So I get negative 1 over negative 1, which is 1. And so what I have obtained is a on the right hand side and 1 on the left hand side, so a equal 1. So we found that a equal 1. To find b, we're going to do the same sort of things. We're going to multiply by x minus 1, in other words by the factor that is under b, and then we'll set that equal to 0, in other words we'll plug x equal 1. So when I multiply by x minus 1, on the left hand side I cross out the factor, on the right hand side I cross it out below b because I have b times x minus 1 divided by x minus 1, so this x minus 1 cancels out. And then I multiply a by x minus 1 and c by x minus 1. When I plug x equal 1, the term a times x minus 1 over x is going to be 0, and similarly c times x minus 1 over x plus 1 is 0, and therefore these two terms disappear, and on the right hand side, just like before, the only thing remaining is b. On the left hand side, I plug x equal 1 in what remains, and I get 1 plus 2 minus 1, 2 at the top, 1 multiplied by 1 plus 1, 2 at the bottom, so I get 2 over 2, in other words 1. So I have 1 on the left hand side, b on the right hand side, and therefore b is 1. Finally, to find c, we proceed similarly, that is, we multiply everything by x plus 1, which is a factor under c, and we set it equal to the value that makes it 0. In other words, we plug x equal negative 1. That way, we have c times x plus 1 over x plus 1, the x plus 1 cancels out, so just c. And for the other two terms containing a and b, we have a factor x plus 1 at the top that we set equal to 0, so these terms disappear and we end up again with only c on the right hand side. On the left hand side, the factor x plus 1 is cancelled out, and we plug x equal negative 1 in what remains. We obtain 1 minus 2 minus 1, so negative 2 at the top, and negative 1 times negative 2 at the bottom. In other words, we get negative 2 over 2, that is negative 1. So c is negative 1. Now what does that mean? The function x squared plus 2x minus 1 divided by x cubed minus x can be rewritten as a over x plus b over x minus 1 plus c over x plus 1, where a and b are 1 and c is negative 1. In other words, we can rewrite our integral this way, and now we have a sum of three terms that are easy to integrate. We get natural log of absolute value of x plus natural log of absolute value of x minus 1 minus natural log of absolute value of x plus 1, all of this up to a constant. Now let's get back to the situation where we're looking for these coefficients a, b, c. I mentioned that an alternative method that is somewhat less efficient in that particular case but applies more systematically is the system method. So let's take a look at what that means. So starting from our equality, now we're going to look at the right hand side. So we have a fraction, a sum of three fractions, namely, that depends on ABC, and we want to find ABC. What we're going to do this time is rewrite this as one fraction. So to do that, we need the common denominator, which is going to be the product x, x minus 1, x plus 1. In doing so, we multiply a by x minus 1 and x plus 1, b by x and x plus 1, and c by x and x minus 1. And this way, we have these three fractions that are all with the same denominator, x, x minus 1, x plus 1. We can add them together, and at the top we have this expression, a, x minus 1, x plus 1, plus bx, x plus 1, plus cx, x minus 1. Now if we look at these two fractions, they have the same denominator, and therefore if they are equal, they should have the same numerator. So we end up with the equality x squared plus 2x minus 1 equal to the numerator of our fraction that depends on ABC. On the left hand side, we have a quadratic function. On the right hand side, we also have a quadratic function, but that is not written in standard form here. So this is what we're going to do, write it in standard form. In other words, write it as x squared times a constant plus x times a constant plus a constant term. For x squared, you see that you have ax times x, you have bx times x, and cx times x. So these are the only ways to get x squared. Therefore, the coefficient of x squared is a plus b plus c. The ways to get a term in x, you have ax times 1 and then negative a times x. So this cancels out, and we don't have any term in x coming from the first term in the sum. Then we have bx times 1 and cx times negative 1. So x has as a coefficient b minus c. Finally, the only way to get a constant term is to multiply a by negative 1 and then the result by 1. So we get negative a for the constant term. Now I have an equality between two polynomials, and the only way this can happen is if they have the same coefficients for the term of corresponding degree. In other words, to have this equality, I need the coefficient of x squared on the right-hand side, which is a plus b plus c, to be equal to the coefficient of x squared on the left-hand side, which is 1. I need the coefficient of x, b minus c, to be equal to the coefficient of x on the left-hand side, which is 2. So b minus c must be 2. And I need the constant coefficients to be equal. In other words, negative a must be negative 1. So that gives us a system of 3 simultaneous conditions. So that's a system of 3 equations with 3 unknowns, and we can solve that for the coefficients. In this case, a is 1, so we can replace a by 1 in the first equation. And the first equation now becomes that b plus c is 0. In other words, b is negative c. And now we have b minus c is 2, so we have negative 2c is 2, in other words c is negative 1, which means b is 1. So we end up with a equal 1, b equal 1, and c equal negative 1, which of course are the same coefficients that we have found by the n-cover method. So now you have seen 2 methods to find these coefficients, and you have some idea of how to apply these methods. We're going to turn to the next video to see more examples.